What if I told you the future of propulsion doesn't rely on burning fuel or spinning turbines, but on harnessing the raw power of the universe itself? Picture this: an engine that doesn't wear out, doesn't need refueling, and runs on the same electrified gas that fuels stars' plasma. It sounds like something straight out of a sci-fi epic, but this is real science, and it's happening right now. For decades, we've been bound by the limits of traditional engines, constrained by fuel shortages, mechanical failures, and the harsh realities of physics. But plasma propulsion shatters those limits, offering a glimpse into a future where engines could run indefinitely, propelling us farther into space than we ever thought possible. Think about the last time you stared up at the night sky, wondering what it would take to reach those distant stars. The answer might just lie in the fourth state of matter, plasma. Unlike solids, liquids, or gases, plasma is ionized, superheated, and brimming with energy. It's the dominant state of matter in the universe, found in lightning bolts, neon signs, and of course, the sun. Now, scientists are tapping into that boundless energy to create engines that don't just push boundaries, they erase them. Imagine spacecraft that don't rely on heavy fuel tanks, but instead draw power from magnetic fields and electric currents, accelerating faster and lasting longer than anything we've built before. This isn't just an upgrade, it's a revolution in how we think about motion, energy, and exploration. So why isn't everyone talking about this yet? Because plasma propulsion is still in its daring, experimental phase, where the brightest minds are racing to solve puzzles that once seemed impossible. The challenges are real, containing something as volatile as plasma, directing its immense energy efficiently, and scaling it for practical use. But the breakthroughs are happening faster than you might think. From lab prototypes to theoretical models that could one day take us to Mars and beyond, the progress is electrifying. And that's exactly what we're diving into today: the science, the stakes, and the stunning potential of plasma-powered engines. By the end of this journey, you'll see why this technology isn't just a footnote in the history of innovation, but a leap toward a future where the sky is no longer the limit. Buckle up, we're about to explore the engines that could keep running long after we're gone. To grasp why plasma is such a game changer for propulsion, let's break down what makes it so extraordinary. Imagine taking a gas and supercharging it with so much energy that its atoms split apart, leaving behind a swirling soup of free electrons and ions. That's plasma, a state of matter where particles are so energized they break free from the usual rules that govern solids, liquids, or gases. What sets plasma apart is its ability to conduct electricity and react to magnetic fields like no other substance. While a regular gas might ignore a magnet, plasma bends to its will, twisting and accelerating in ways that can be precisely controlled. This isn't just theoretical, it's the same force that shapes solar flares and lights up neon signs. Now, think about how traditional rockets work. They burn fuel, creating hot gas that shoots out the back to push the vehicle forward. But plasma propulsion flips that idea on its head. Instead of relying on chemical reactions, it uses magnetic fields to accelerate ionized particles at mind-blowing speeds, sometimes 10 times faster than conventional engines. That means more thrust with far less fuel, a critical advantage when every gram counts in space travel. And because plasma doesn't rely on moving parts or combustion, the risk of mechanical failure drops dramatically. It's like comparing a steam engine to a lightning bolt. One is bound by friction and fuel, while the other harnesses pure, raw energy. But here's where it gets even more fascinating. Plasma isn't just efficient, it's nearly limitless. In space where sunlight can power solar panels, a plasma engine could theoretically run for years without refueling. Picture a spacecraft that doesn't need to carry massive fuel tanks, freeing up weight for more instruments, crew supplies, or even larger missions. This is why agencies like NASA and private aerospace companies are pouring resources into plasma research. From ion thrusters already nudging satellites into position to experimental designs that could one day propel humans to Mars, the applications are as vast as the cosmos itself. The science is complex, sure, but the payoff, a future where engines never stop, is worth every breakthrough. The difference between plasma and traditional rocket engines isn't just about power, it's a fundamental shift in how we think about motion in space. Take chemical rockets, the workhorses of space exploration for decades. They operate on a simple but brutal principle: burn fuel explosively and use that energy to hurl a spacecraft forward. It's like lighting a firework, spectacular, yes, but over in seconds, leaving you with nothing but smoke and empty fuel tanks. That's why missions like the Apollo moon landings required monstrous rockets just to carry enough fuel for a short trip. The math is unforgiving. The more fuel you pack, the heavier your spacecraft becomes, which means you need even more fuel just to lift that extra weight. It's a vicious cycle that keeps us tethered to short-range missions. Now, contrast that with plasma propulsion. Instead of relying on explosive chemical reactions, these engines use electromagnetic fields to accelerate ionized particles to staggering speeds, sometimes exceeding 100,000 miles per hour. Think of it like a cosmic slingshot, where particles are flung backward with such precision that the thrust builds gradually but relentlessly. The result: a spacecraft that doesn't just leap off the launch pad but glides through space with the efficiency of a sailboat riding the wind. While a chemical rocket might burn all its fuel in minutes, a plasma engine can run for months or even years on the same energy supply, as long as it has electricity from solar panels or a nuclear source. That's the kind of endurance we need for missions to Mars, the outer planets, or beyond. But here's where the real magic happens. Traditional rockets are limited by the energy stored in their fuel. Once it's gone, there's no more thrust. Plasma engines, though, could theoretically keep running indefinitely if they have access to a power source. Imagine a future where spacecraft refuel not by docking with a gas station, but by skimming the solar wind or tapping into distant starlight. This isn't just incremental progress, it's a complete reimagining of what's possible in space travel. We're talking about probes that could explore the outer reaches of the solar system without worrying about fuel shortages, or crewed ships that make the journey to Alpha Centauri a realistic goal rather than a pipe dream. The implications are staggering, and they're closer than you might think. Of course, plasma engines aren't perfect yet. They can't match the raw thrust of chemical rockets, which is why we still rely on them for liftoff from Earth. But once in space, where efficiency matters more than brute force, plasma propulsion shines. Satellites already use ion thrusters to adjust their orbits with pinpoint precision, and NASA's Dawn mission proved the technology's potential by visiting 2 asteroids on a single tank of fuel, something impossible with traditional engines. The race is now on to scale this technology for larger missions, solving challenges like power generation and plasma containment. Every breakthrough brings us closer to a new era of exploration, where the stars aren't just destinations but waypoints on an endless journey. The question isn't whether plasma engines will change space travel, it's how soon we'll let them. At the heart of every plasma thruster lies a beautifully simple yet profoundly powerful principle: turning gas into lightning. Here's how it works in practice. Engineers start with a neutral gas like xenon, chosen for its heavy atoms and ease of ionization, and blast it with electrons until its atoms split apart. This creates a soup of positively charged ions and free electrons, the very essence of plasma. But the real magic happens next. Instead of letting this energetic chaos dissipate, they channel it using electromagnetic fields, which act like invisible rails guiding the ions toward the engine's exit at breathtaking speeds. As these ions shoot out into space, their expulsion creates an equal and opposite force, thrust that pushes the spacecraft forward with remarkable precision. What makes this process so revolutionary is its elegance compared to the brute force approach of chemical rockets. Traditional engines rely on the explosive energy of burning fuel, which is inherently messy and inefficient. Plasma thrusters, on the other hand, operate with the finesse of a conductor leading an orchestra. The ions move in perfect harmony, accelerated not by fire but by the silent, invisible pull of magnetic fields. This eliminates the need for bulky fuel tanks and reduces wear and tear, since there are no moving parts to break down. It's like trading a sledgehammer for a scalpel, delicate, controlled, and far more adaptable to the demands of long-duration spaceflight. But efficiency isn't the only advantage. Plasma thrusters offer something even more valuable: consistency. Chemical rockets deliver their thrust in short, violent bursts, like a sprinter gasping for breath after a sprint. Plasma engines, though, provide a steady, whisper-quiet push, more like a marathon runner pacing themselves for the long haul. This makes them ideal for missions where patience is a virtue, such as maintaining a satellite's orbit for years or gently nudging a deep space probe toward a distant asteroid. NASA's Dawn mission, which visited Ceres and Vesta, showcased this perfectly. By relying on ion thrusters, Dawn achieved what no chemical rocket could, exploring multiple celestial bodies on a single mission without running out of fuel. Yet for all their promise, plasma thrusters aren't without challenges. Their Achilles heel is thrust density, the sheer force they can produce at any given moment. While chemical rockets can generate enough power to escape Earth's gravity in minutes, plasma engines build their speed gradually, making them unsuitable for liftoff. But once in space, where time and efficiency outweigh raw power, they shine. Researchers are already working on next-generation designs, like magnetoplasmadynamic thrusters, which could bridge this gap by producing stronger thrust without sacrificing efficiency. The future might even see hybrid systems, where chemical rockets handle launch and plasma engines take over for the journey beyond. The implications stretch far beyond our current reach. Imagine probes that could tour the solar system on a single tank of fuel, or crewed ships that make the trip to Mars with reserves to spare. With each breakthrough, we're not just improving engines, we're redefining what's possible in human exploration. Plasma propulsion isn't just another step forward. It's the key to unlocking a universe where distance is no longer a barrier, but an invitation. While plasma propulsion might sound like a single groundbreaking idea, the reality is far more nuanced and exciting. Different types of plasma engines are emerging, each tailored for specific challenges in space exploration. Take ion thrusters, for example. These are the quiet workhorses of modern spaceflight, already proven in missions like NASA's Dawn spacecraft. By ionizing xenon gas and accelerating the particles with electric fields, they generate gentle but relentless thrust, perfect for fine-tuning satellite orbits or powering long-duration probes. Their efficiency is unmatched, but they trade raw power for endurance, making them the tortoises of the propulsion world, slow and steady but unstoppable over time. Then there's the magnetoplasmadynamic thruster, or MPD, a beast of a machine designed for higher power demands. Imagine replacing the delicate electric fields of an ion thruster with roaring magnetic currents that whip plasma into a frenzy, producing far stronger thrust. These engines are like the dragsters of space propulsion, capable of faster acceleration, ideal for crewed missions where time matters, the trade-off. They guzzle energy, requiring power sources far beyond today's solar panels. But with advances in nuclear reactors or beamed energy, MPD thrusters could become the backbone of interplanetary travel, bridging the gap between patience and speed. But the true crown jewel of plasma propulsion lies in fusion-driven engines. Here, we're not just ionizing gas, we're replicating the power of stars themselves. Picture a reactor that fuses hydrogen atoms into helium, unleashing torrents of energy while producing plasma as a byproduct. This isn't just propulsion, it's a self-sustaining powerhouse capable of generating thrust and electricity indefinitely. The implications are staggering: spacecraft that could journey for decades, fueled only by the lightest element in the universe. While still in its experimental infancy, fusion propulsion represents the ultimate frontier, where the line between engine and star begins to blur. The diversity of these designs isn't accidental. Each fills a critical niche in humanity's push into space. Ion thrusters excel in robotic exploration, where efficiency trumps speed. MPD thrusters could dominate the era of interplanetary commerce, ferrying cargo and crews between Mars and Earth. And fusion, that's the key to the stars themselves, turning science fiction into tomorrow's flight plans. What unites them all is a shared promise: propulsion that defies the old limits, rewriting the rules of where we can go and how long we can stay there. The race isn't just about building better engines, it's about choosing the right tool for the next giant leap. Right now, in the silent expanse of space, plasma engines are quietly proving their worth. Take NAS, a next-sea ion thruster, a marvel of engineering that's already steering missions like the Double Asteroid Redirection Test, or DART. This unassuming engine, no larger than a car tire, uses xenon plasma to deliver precise, fuel-efficient thrust perfect for nudging a spacecraft onto a collision course with an asteroid. Over in Europe, the T6 thruster, developed by the European Space Agency, is doing similar work aboard missions like BP Colombo, which is threading its way toward Mercury with the patience of a cosmic sculptor. These aren't prototypes gathering dust in a lab. They're the unsung heroes of modern spaceflight, turning what was once science fiction into routine operation. What makes these engines so indispensable? It's their ability to turn scarcity into abundance. Traditional satellites often waste precious fuel just staying in orbit, battling drag and gravity in a slow, expensive dance. Plasma thrusters flip that equation. By sipping fuel instead of guzzling it, they can keep communication satellites humming for years longer than expected, saving billions in replacement costs. The Dawn mission, which toured the asteroid belt on a single tank of xenon, demonstrated this perfectly. While chemical rockets would have left it stranded after one destination, Dawn's ion thrusters let it hop from Vesta to Ceres like a celestial tourist, rewriting the playbook for deep space exploration. But the real excitement lies in what's coming next. Private companies like SpaceX and Blue Origin are eyeing plasma propulsion for future lunar and Mars missions, where efficiency could mean the difference between a one-way trip and a sustainable presence. Imagine a lunar base supplied by cargo ships with plasma engines, their fuel tanks still half full after landing. Or consider the proposed Interstellar probe, a mission that could use next-gen ion thrusters to reach the edge of our solar system in record time, powered by nothing but sunlight and ingenuity. The stakes go beyond mere efficiency. Every kilogram of fuel saved is a kilogram of scientific instruments, life support systems, or crew supplies that can be added to a mission. That's why agencies worldwide are racing to refine this technology. From Japan's innovative microwave-powered thrusters to experimental designs that could one day harness nuclear reactors for even greater power. The quiet hum of plasma engines might not have the drama of a rocket launch, but their legacy will be written in the decades-long missions they enable and the worlds they'll help us reach. Scaling plasma engines from small satellite thrusters to the massive powerhouses needed for crewed missions is like trying to turn a campfire into a controlled wildfire, possible but fraught with challenges. The tiny ion thrusters used today are engineering marvels, no doubt, but they're designed for precision, not power. A satellite might need only a whisper of thrust to adjust its orbit, but a crewed spacecraft heading to Mars demands something far more robust. The first hurdle, energy. Plasma thrusters are energy hungry, and scaling them up means finding ways to deliver megawatts of power, enough to light up a small town, without turning the spacecraft into a flying power plant. Solar panels, which work beautifully for small probes near the sun, simply can't keep up with the demands of a Mars-bound ship. That's why researchers are exploring nuclear reactors or even compact fusion generators as potential solutions, though each comes with its own set of technical and safety hurdles. Then there's the heat. Plasma doesn't just generate thrust, it radiates enough heat to melt conventional engine components. Small thrusters manage this by operating at lower power levels, but a crewed mission would require engines running at temperatures rivaling the surface of the sun. Advanced materials like tungsten or ceramic composites are being tested to withstand these extremes, but even they have limits. The real breakthrough might come from active cooling systems, where liquid metals or gases circulate through the engine, absorbing heat before it can cause damage. Imagine a network of microscopic veins threading through the thruster, constantly dissipating heat like a high-tech sweat gland. This isn't just theory. Labs are already prototyping these systems, pushing materials science to its absolute limits. But perhaps the trickiest challenge of all is containment. Plasma at the scales needed for crewed missions is like trying to bottle a lightning storm. The magnetic fields required to control it must be exponentially stronger and more precise than those used in today's thrusters. Superconducting magnets, which lose all electrical resistance at ultra-low temperatures, offer a tantalizing solution. These magnets can generate fields powerful enough to corral the plasma, but they come with a catch. They need to be cooled to near absolute zero, requiring bulky cryogenic systems that add weight and complexity. Some engineers are betting on high-temperature superconductors, which operate at less extreme, though still frigid temperatures, as a middle ground. Others are experimenting with entirely new configurations, like rotating magnetic fields or plasma pinches, where the particles are squeezed into a stable column by their own electromagnetic forces. The stakes couldn't be higher. Solve these problems and you unlock engines capable of cutting the travel time to Mars from months to weeks, a game changer for astronaut health and mission safety. Longer trips mean more exposure to cosmic radiation and zero gravity, both of which pose serious risks. But with a high-powered plasma engine, you could reduce those risks dramatically, making interplanetary travel not just possible but practical. Private companies and space agencies alike are racing to crack these challenges, from NASA advanced propulsion labs to startups developing revolutionary reactor designs. The path forward is far from certain, but the potential rewards, a solar system within humanity's reach, are worth every obstacle. The dream isn't just bigger engines, it's a future where the vast distances between worlds feel a little smaller and the stars a little closer. Keeping plasma under control is like trying to tame a hurricane with nothing but a net made of magnets. It sounds impossible until you see how far we've come. The secret lies in magnetic confinement, a technique borrowed from the world of fusion reactors where scientists have spent decades wrestling with the same challenge. Picture this, a superheated plasma stream hotter than the surface of the sun, trapped inside a cage of invisible magnetic fields. These fields don't just contain the chaos, they sculpt it, bending the plasma into stable shapes that can be directed with precision. It's a dance of physics and engineering, where even the slightest misstep could mean losing control entirely. Recent breakthroughs in superconducting magnets are changing the game. Unlike ordinary magnets, which lose their power under extreme conditions, superconductors can generate fields strong enough to hold plasma in place indefinitely, as long as they're kept at temperatures colder than deep space. Engineers are now designing compact cryogenic systems that make this feasible even on spacecraft, where every gram and watt counts, but magnets alone aren't enough. Plasma has a mind of its own, twisting and kinking in ways that can break containment. That's where advanced algorithms come in, constantly adjusting the magnetic fields in real time to counteract instabilities before they escalate. Think of it like a high-stakes balancing act, where supercomputers and sensors work together to predict and correct the plasma's every move. The payoff for mastering this could redefine space travel. Traditional engines degrade over time, their components eroded by heat and friction. But a well-confined plasma thruster could theoretically run for decades without wearing out, its performance limited only by the durability of its power source. Imagine a deep space probe that arrives at Pluto with the same efficiency it had leaving Earth, or a Mars-bound ship that doesn't need spare parts for the journey back. These aren't just incremental improvements, they're the kind of leaps that turn science fiction into mission plans. Yet the challenges remain as daunting as they are thrilling. Scaling magnetic confinement for larger engines means solving puzzles like power consumption and heat dissipation, problems that have stumped researchers for years. But with every experiment, whether in labs or aboard the International Space Station, we're learning how to push plasma a little closer to obedience. The day we crack this code completely, the engines we build won't just take us to new worlds, they'll keep running long after we've left them behind, silent sentinels in the endless dark. Nuclear fusion has long been the holy grail of clean energy here on Earth, but its potential for space propulsion is even more breathtaking. Picture an engine that doesn't just sip fuel but creates it from scratch, fusing hydrogen atoms into helium while generating plasma as a byproduct. This isn't just propulsion, it's a self-sustaining star in a bottle, capable of hurling spacecraft across the solar system at speeds we've only dreamed of. Projects like Princeton's Field Reversed Configuration Reactor aren't just theorizing about this future, they're building it, one magnetic coil at a time. By trapping superheated plasma in a donut-shaped magnetic field, they're mimicking the conditions inside the sun, where fusion occurs naturally. The result: a power source that could run for years on nothing but the lightest elements in the universe. What sets fusion apart from other plasma propulsion methods is its sheer density of energy. While ion thrusters excel in efficiency, they lack the punch needed for crewed missions. Fusion bridges that gap, offering thrust levels closer to chemical rockets but with the endurance of plasma engines. Imagine a spacecraft accelerating continuously for months, reaching Mars not in half a year but in just 6 weeks. The difference isn't just about speed, it's about survival. Shorter trips mean less exposure to cosmic radiation, less muscle atrophy for astronauts, and fewer supplies needed for the journey. Suddenly, the red planet isn't a distant outpost but a feasible destination for regular travel. The engineering hurdles, of course, are monumental. Fusion requires temperatures hotter than the sun's core, over 100 million degrees, and pressures that would crush conventional materials. Containing that fury demands advances in superconductors and plasma stability that are still in their infancy, but the progress is undeniable. Private companies like Helion Energy are already testing compact fusion reactors that could fit inside a spacecraft, while NASA's Innovative Advanced Concepts program funds wild ideas like the fusion-driven rocket, which aims to channel fusion explosions into directed thrust. These aren't just lab curiosities, they're stepping stones to a paradigm where every mission carries its own miniature star, burning clean and bright against the void. The implications ripple far beyond propulsion. A fusion-powered ship wouldn't just move faster, it could support colonies indefinitely, using excess energy to manufacture fuel, recycle air, and even shield crews from radiation with magnetic fields. Lunar bases, asteroid mines, and Martian cities would no longer depend on fragile supply chains from Earth. Instead, they'd tap into the same boundless energy that lights the cosmos. This is the promise of fusion propulsion, not just faster engines, but a fundamental shift in how humanity inhabits space. The challenges are staggering, yes, but so were the obstacles to landing on the moon until we did it. The stars have always been fusion engines. Now it's our turn to learn how they work. Powering plasma engines isn't just about creating thrust, it's about keeping the lights on in the harshest environments imaginable. Near Earth or the inner solar system, sunlight is abundant, and solar panels can efficiently convert those rays into the electricity needed to ionize gas and sustain plasma. Take NASA's Dawn spacecraft, for example. Its massive solar wings, spanning nearly 20 meters, harvested enough energy to power its ion thrusters for over a decade, allowing it to explore the asteroid belt without ever running out of juice. Solar is elegant, reliable, and perfect for missions where sunlight is plentiful, but venture farther out where the sun shrinks to a mere speck and the math changes dramatically. Beyond the orbit of Mars, sunlight becomes too faint for solar panels to deliver meaningful power. This is where nuclear energy steps in not as a backup, but as a necessity. Radioisotope thermoelectric generators, or RTG, have been the quiet heroes of deep space exploration for decades. These devices convert the heat from decaying radioactive materials like plutonium-238 directly into electricity. No moving parts, no solar arrays, just steady, dependable power for years on end. The Voyager probes, now drifting in interstellar space, still whisper back to Earth thanks to RTGs that have outlived their original mission timelines by decades. For plasma engines, this consistency is gold. A thruster powered by an RTG could theoretically run for centuries, pushing probes to the outer planets or even neighboring star systems without ever needing a refuel. But RTGs have limits. They're low-power devices, fine for small scientific instruments, but often insufficient for the energy-hungry demands of high-thrust plasma engines. That's where compact fission reactors enter the picture. Unlike RTGs, which passively decay, fission reactors actively split atoms to release staggering amounts of energy. Imagine a reactor the size of a trash can, generating enough electricity to power a small town. Now shrink that down to fit inside a spacecraft. NASA's Kilopower project has already demonstrated reactors capable of producing up to 10 kilowatts continuously for 10 years. Enough to sustain a crewed Mars mission or propel a plasma-driven cargo ship across the solar system. The beauty of fission is its scalability. Need more power, just add fuel rods. Suddenly, missions that seemed impossible, like human exploration of the icy moons of Jupiter, become plausible. The choice between solar and nuclear isn't just about distance, it's about purpose. Solar excels in predictability and simplicity, ideal for robotic explorers patrolling the inner solar system. Nuclear, though more complex, unlocks the outer reaches and beyond where darkness and cold dominate, but the future might not force a choice at all. Hybrid systems could combine the best of both: solar panels for maneuvering near planets, supplemented by a reactor for the long void between them. Picture a spacecraft that unfurls solar sails to cruise past Venus, then fires up its fission core to sprint toward Saturn. The stakes are higher than mere engineering preferences. Solar-dependent missions are limited by the sun's fading glow, while nuclear-powered ships could roam indefinitely, tethered only by the laws of physics. As we push plasma propulsion to its limits, the energy source we pick won't just determine how far we go, it'll define how long we stay there. Whether it's sunlight or atoms that fuel our engines, one thing's certain: the era of endless propulsion is no longer a question of if, but when. The idea of crossing the vast emptiness between stars has haunted humanity for generations, a challenge so immense it seemed locked in the realm of fiction. But plasma propulsion is rewriting those limits, turning interstellar travel from a poetic dream into an engineering puzzle we're finally equipped to solve. Consider the numbers. Even our fastest chemical rockets would take tens of thousands of years to reach the nearest star, Proxima Centauri. Plasma engines, though, could slash that timeline dramatically. By accelerating particles to a fraction of light speed, they offer a way to traverse light years within a human lifetime. The catch: sustaining that thrust long enough to matter. This is where fusion-driven plasma engines enter the picture. Unlike conventional ion thrusters, which rely on external power sources, fusion reactors could generate both energy and thrust in one self-contained system. Picture a spacecraft that carries its own miniature sun, fusing hydrogen into helium and channeling the resulting plasma into a directed exhaust. The fuel supply would be virtually limitless. Just scoop up hydrogen from interstellar space as you go, like a cosmic whale filtering krill. Projects like the Princeton Field Reversed Configuration Experiment are already testing compact fusion reactors that could fit aboard a ship, proving the concept isn't just theoretical. The math is compelling. A fusion-powered vessel could reach 20% of light speed, cutting the journey to Proxima Centauri from millennia to mere decades. Yet the hurdles are as vast as the distances involved. Scaling fusion to spacecraft size demands breakthroughs in magnetic confinement and heat management that still elude us. And then there's the human factor. Even at 20% light speed, a crewed mission would face decades in deep space, with all the psychological and biological risks that entails. That's why initiatives like Breakthrough Starshot focus on unmanned probes, gram-scale crafts pushed by ground-based lasers to relativistic speeds. These starships could reach Proxima Centauri in just 20 years, beaming back data at the speed of light. It's a clever workaround, but for those dreaming of footsteps on alien worlds, plasma-powered crewed ships remain the ultimate prize. The timeline might surprise you. While interstellar travel still sounds futuristic, the foundational technologies are advancing faster than many realize. Private ventures like Helion Energy are racing toward net-positive fusion reactors, and NASA ongoing plasma propulsion experiments hint at near-term scalability. Optimistic projections suggest a prototype interstellar probe could launch within the next 50 years, well within the lifetime of many watching this. The gap between today's lab prototypes and tomorrow's star-faring vessels isn't a chasm. It's a series of solvable problems, each one bringing us closer to the stars. What makes this moment pivotal isn't just the technology, it's the shift in mindset. For centuries, interstellar travel was dismissed as impossible, a fantasy for distant generations. Now it's a question of when, not if. The equations work, the physics checks out. All that's left is the gritty, glorious work of engineering our way forward. Whether it's a fusion-powered arc or a laser-accelerated microprobe, the first mission to another star will likely ride on a stream of superheated plasma, proof that the universe's most abundant state of matter might also be the key to exploring it. The stars aren't waiting, and thanks to plasma engines, neither are we. Earth's orbit is becoming a cosmic junkyard, littered with the remnants of decades of space exploration, discarded rocket stages, defunct satellites, and countless fragments spinning uncontrollably at thousands of miles per hour. Every time a traditional rocket launches, it leaves behind a trail of debris, some of which lingers for centuries, but plasma engines offer a way out of this mess. Unlike chemical rockets that jettison empty fuel tanks or rely on explosive separation charges, plasma propulsion systems operate with surgical precision, minimizing the risk of creating new debris. A satellite with a plasma thruster doesn't need violent maneuvers to adjust its course. It can glide gracefully into position, fine-tuning its orbit with near-silent efficiency. The difference isn't just about avoiding clutter, it's about active cleanup. Imagine a future where aging satellites, instead of becoming hazards, use their plasma thrusters to deorbit themselves at the end of their missions. With pinpoint control, they could steer into the atmosphere to burn up harmlessly, leaving no trace behind. This isn't hypothetical. The European Space Agency's Aeolus satellite recently pioneered this very approach, using an ion engine to guide itself to a controlled re-entry. Contrast that with traditional satellites, which often drift for years before tumbling unpredictably back to Earth, posing risks to both other spacecraft and people below. But the real game changer lies in collision avoidance. Space debris isn't just static trash, it's a high-speed domino effect waiting to happen. A single collision can spawn thousands of new fragments, each capable of triggering further impacts, a cascading nightmare known as the Kessler syndrome. Plasma thrusters give satellites the agility to dodge these threats with minimal fuel expenditure, while a chemical-powered satellite might reserve precious propellant for emergencies. A plasma-equipped craft could make constant micro-adjustments, sidestepping debris with the ease of a dancer avoiding obstacles. The environmental stakes extend beyond Earth's orbit. Deep space missions powered by plasma could also reduce pollution in less obvious ways. Traditional rockets rely on toxic fuels like hydrazine, which can contaminate launch sites and pose health risks to ground crews. Plasma engines, though, often use inert gases like xenon or argon, substances as harmless as the air in a neon sign. Even their exhaust is cleaner. Instead of spewing reactive chemicals, they emit only ionized particles that disperse harmlessly into the vacuum. As space becomes increasingly crowded, the need for sustainable propulsion isn't just idealistic, it's urgent. Companies like SpaceX and OneWeb are already planning mega constellations of thousands of satellites, and without cleaner alternatives, low Earth orbit could become unnavigable within decades. Plasma technology offers a path forward, not just as a tool for exploration, but as a steward for the space environment. The next era of spaceflight won't just be about going faster or farther, it'll be about leaving behind a cosmos we can continue to explore, not one buried beneath our own debris. Right now, blasting a single kilogram of payload into orbit costs tens of thousands of dollars, a price tag that's kept spaceflight the exclusive domain of governments and billionaire-backed companies. But plasma propulsion could rewrite that equation entirely. Traditional rockets waste staggering amounts of energy hauling their own fuel, a vicious cycle where more fuel means more weight, which demands even more fuel just to lift it. Plasma engines break that loop. By squeezing 10 times the efficiency out of every gram of propellant, they slash the fuel burden so dramatically that launch costs could plummet by orders of magnitude. Picture a future where sending satellites into space costs less than manufacturing them, where universities, startups, and even developing nations can afford regular access to orbit. The savings don't stop at the launch pad. Satellites equipped with plasma thrusters live longer, too. Without the need to reserve fuel for years of orbital adjustments, they can dedicate every drop of propellant to mission-critical tasks. Telecommunications networks could keep their constellations aloft for decades, passing the savings on to consumers. Earth observation satellites could monitor climate change or natural disasters without budget-busting replacement costs. Even the Hubble Space Telescope, which required multiple expensive shuttle missions to service, might have lasted its entire lifespan on a single tank of plasma fuel. The economic ripple effects would be profound, transforming space from a high-stakes gamble into a sustainable investment. But the real game changer lies in the industries this affordability could unlock. Asteroid mining, once a pipe dream, becomes plausible when fuel efficiency makes round trips to the asteroid belt feasible. Imagine robotic prospectors harvesting platinum or rare earth metals, their plasma drives enabling frequent cargo runs back to Earth. Lunar bases could shift from symbolic outposts to bustling hubs, resupplied by efficient plasma-powered freighters rather than disposable rockets. Every dollar saved on propulsion is a dollar that can fund new experiments, better instruments, or more ambitious missions. Perhaps the most exciting prospect is the democratization of space itself. When launches cease to be multi-million-dollar spectacles, smaller nations and private entities gain a seat at the table. A university in Nairobi could launch its own climate satellite. A startup in Buenos Aires might deploy a swarm of low-cost space telescopes. The barrier to entry crumbles, unleashing a global wave of innovation. We've seen this story before when personal computers shrank from room-sized mainframes to laptops. They didn't just get cheaper, they unlocked revolutions no one could predict. Plasma propulsion could do the same for the final frontier, turning space from an exclusive club into a playground for all of humanity. The numbers tell the tale. A single Falcon 9 rocket carries over 400 metric tons of fuel for a launch. Replace that with a plasma-driven system, and you'd need just a fraction of the mass, freeing up payload capacity for more satellites, more science, or more ambitious deep space missions. Companies like Momentus and Acheon Systems are already proving this with tiny plasma thrusters that fit on shoebox-sized satellites, reducing reliance on expensive ride-share launches. As the technology scales, so will the savings, eventually reaching a tipping point where space access isn't just affordable but routine. The economic impact won't just reshape aerospace, it'll redefine what's possible for our species among the stars. The same breakthroughs making plasma engines revolutionary for space exploration are quietly transforming military strategy in ways most civilians never see. Imagine a reconnaissance satellite that can loiter for years over a hotspot, adjusting its orbit with silent precision, no telltale engine flares to betray its position. That's the stealth advantage plasma thrusters offer. Unlike traditional chemical rockets, which leave visible exhaust plumes, ion and plasma engines emit nothing but a faint blue glow, virtually undetectable from the ground. For military planners, this isn't just about efficiency, it's about survivability in an era where space itself is becoming a contested frontier. Now consider orbital response times. Today, repositioning a satellite to monitor a sudden crisis, say, a missile launch or troop movement, can take days or weeks with conventional propulsion. Plasma engines slash that timeline dramatically. A vehicle equipped with high-power magnetop-aerodynamic thrusters could shift orbits in hours, providing real-time intelligence when it matters most. The U.S. Air Force's X-37B spaceplane has already tested experimental propulsion systems that hint at this future, and defense contractors like Lockheed Martin are actively developing next-gen plasma drives under classified programs. The goal, a fleet of agile spacecraft capable of outmaneuvering adversaries in the ultimate high ground, but the applications extend far beyond satellites. Picture unmanned aerial vehicles that don't need to land for fuel, drones powered by compact plasma thrusters, drawing energy from airborne lasers or microwave beams. These could maintain position over conflict zones for months, serving as persistent eyes in the sky without risking pilot lives. The Pentagon's Defense Advanced Research Projects Agency has floated concepts like this under projects like the Endless Loiter program, where endurance is the ultimate weapon. Even ground-based missile defense could benefit. Plasma-powered interceptors, faster and more maneuverable than traditional rockets, might one day swat hypersonic missiles from the sky with pinpoint accuracy. Of course, with great power comes great responsibility and geopolitical tension. The same technology enabling cleaner space exploration could also fuel an arms race in orbit. Anti-satellite weapons propelled by plasma engines would be harder to detect and faster to strike, raising stakes for global security. International treaties currently limit weapons in space, but the line between defensive and offensive systems blurs quickly. A satellite capable of dodging debris could just as easily evade an incoming missile or position itself to disable another nation's spacecraft. This duality isn't lost on policymakers. While NASA explores plasma propulsion for Mars missions, agencies like the Space Force are investing in parallel research, ensuring national security keeps pace with innovation. The challenge lies in balancing progress with restraint, harnessing plasma's potential without triggering a new era of orbital conflict. One thing's certain, as the technology matures, it won't just redefine how we explore space, but how we protect or threaten the fragile peace among the stars. The future of propulsion isn't merely a scientific endeavor, it's a strategic pivot point with ramifications far beyond the launch pad. While government agencies laid the foundation for plasma propulsion, private companies are now sprinting ahead with the urgency only competition can fuel. At the forefront is Ad Astra Rocket Company, founded by former NASA astronaut Franklin Chang Diaz, who spent decades perfecting his variable specific impulse magnetoplasma rocket concept. Their Vasima engine isn't just theoretical, it's been tested aboard the International Space Station, demonstrating plasma's potential in real-world conditions. What sets Vasima apart is its ability to dial up thrust like a volume knob, switching between high-efficiency cruising and bursts of acceleration when needed. It's the closest thing we have to a cosmic gas pedal, blending the endurance of ion thrusters with the flexibility of chemical rockets. Then there's SpaceX, which has quietly integrated plasma technology into its Starlink satellites. Though Elon Musk's company is better known for its roaring Falcon rockets, their use of Hall effect thrusters, a type of plasma engine, reveals a long-game strategy. Each Starlink satellite relies on these compact, krypton-fueled thrusters to maintain orbit and avoid collisions, creating a self-adjusting megaconstellation that would be economically impossible with traditional propulsion. The scale is staggering, thousands of satellites, each with its own miniature plasma drive, forming what amounts to the largest fleet of ion-powered spacecraft in history. But the innovation doesn't stop there. Startups like Achean Systems are miniaturizing plasma thrusters to fit on smartphone-sized CubeSats, democratizing access to advanced propulsion. Their tiled ionic liquid electrospray technology works like a microscopic inkjet printer, spraying charged droplets to generate thrust with unprecedented precision. Meanwhile, European firm ThrustMe recently launched the first iodine-fueled plasma thruster, a breakthrough that sidesteps the expensive xenon gas most systems rely on. Iodine is not only cheaper but stores as a solid, simplifying spacecraft design. These aren't incremental tweaks, they're reinventions of how propulsion works at the most fundamental level. What makes private sector involvement so transformative is the willingness to take risks that bureaucratic agencies can't. While NASA must justify every dollar to taxpayers, companies like Momentus or Phase 4 can pivot overnight, testing radical ideas like water-based plasma thrusters or wireless power beaming to engines. The pace is electrifying. Where government programs move in decade-long cycles, startups iterate in months. When SpaceX's Starship eventually integrates plasma drives for deep space missions, a near certainty given their patents in the field, the marriage of brute force launch capacity with precision propulsion could redefine interplanetary logistics. The race isn't just about technology, it's about economics. Plasma engines promise to slash the cost of keeping satellites operational, a market worth billions annually. Companies like Amazon's Project Kuiper and OneWeb aren't just watching their pouring resources into proprietary thruster designs, knowing that even a 10% efficiency gain could mean dominance in the global broadband wars. The winners of this quiet propulsion revolution won't just build better engines, they'll control the infrastructure of tomorrow's space economy. And with venture capital flooding into fusion startups like Helion and TA Technologies, the line between transportation and energy production is blurring fast. The age of plasma propulsion isn't coming, it's already here, fueled by the relentless innovation of those willing to bet big on the future. NASA Artemis program isn't just about returning humans to the moon, it's about building a highway to the stars, and plasma propulsion could be the asphalt paving that celestial road. Picture this, lunar landers shuttling between Earth's orbit and the moon's surface, not with explosive chemical burns, but with the smooth, sustained push of ionized gas. The beauty lies in endurance. While traditional rockets might get astronauts to lunar orbit in days, plasma-powered vehicles could keep supply lines open for years, ferrying oxygen, water, and building materials with the efficiency of an electric semi-truck hauling freight cross-country. This changes everything for sustainability. Instead of disposable rockets littering space with debris, we'd have reusable plasma tugs making hundreds of trips on a single fuel load. Take NASA's Next-C ion thruster, already proving its worth on missions like DART. This isn't lab-bound theory, it's flight-tested hardware, capable of running continuously for years while sipping xenon fuel like a Prius sips gasoline. What makes Next-C so pivotal for Artemis is its scalability. The same fundamental technology could power everything from gateway stations' orbital adjustments to cargo ferries supporting the first lunar base. And when the time comes to push farther, those same thrusters, scaled up and paired with nuclear power sources, could propel the first crewed missions to Mars without requiring impractical amounts of propellant. The agency's long-term vision reveals even grander ambitions. Deep space habitats, those spinning, self-contained worldships meant to sustain astronauts on multi-year journeys, depend on propulsion systems that won't quit. Chemical rockets would leave these floating cities stranded after departure, but plasma engines could course correct en route, dodge micrometeoroids, and even generate artificial gravity by rotating tethered modules using precise thrust differentials. NASA's concept for a Mars transit habitat already incorporates high-efficiency electric propulsion for exactly these scenarios, turning what was once science fiction into PowerPoint slides for mission planners. What often goes unnoticed is how plasma tech complements other futuristic NASA initiatives. those sleek solar sails being tested to harness sunlight. Pair them with plasma thrusters for maneuvering, and suddenly you've got hybrid ships that can cruise on photons yet adjust trajectory without waiting weeks for passive solar pressure to nudge them. The nuclear thermal propulsion systems in development, they could provide the initial boost from Earth, then hand off to plasma engines for the marathon middle leg of interplanetary voyages. This isn't about choosing one technology over another. It's about orchestrating them into a symphony of propulsion, where plasma handles the sustained, delicate notes others can't reach. The timeline makes this more than theoretical. NASA's technology roadmap for space propulsion explicitly targets advanced electric propulsion systems, including plasma, as critical for crewed Mars missions by the 2030s. Private partners like Aerojet Rocketdyne are already under contract to develop higher power thrusters, while academic institutions refine plasma containment techniques that could triple efficiency. Every test firing at Glenn Research Center's vacuum chambers, every data packet beamed back from deep space probes using ion thrusters, brings that Mars dream closer. The writing isn't just on the wall, it's in the engine plumes of prototypes, proving that when humanity takes its next giant leap, it won't be on the back of fireworks, but on the steady blue glow of harnessed starlight. The race to perfect plasma propulsion isn't confined to any single nation. It's a symphony of global ingenuity, where shared breakthroughs amplify humanity's reach into the cosmos. Over in Europe, the ESA's Advanced Electric Propulsion System is setting new standards for efficiency, with thrusters like the T6 already powering missions such as BP Colombo through the solar system. These engines, meticulously refined over decades, embody a quiet revolution, the shift from national prestige to collective progress. Meanwhile, Russia's Roscosmos has quietly been pushing boundaries with stationary plasma thrusters like the SPT-100, a workhorse used on countless satellites since the Soviet era. Their expertise in magnetic confinement, honed through years of fusion research, offers unique insights into stabilizing superheated plasma, lessons that could benefit every spacefaring nation. China's rapid ascent in space technology includes ambitious plasma propulsion projects, with institutions like the Lanzhou Institute of Physics testing Hall effect thrusters for future lunar and Mars missions. What makes their approach intriguing is the integration of AI to optimize plasma flow, a fusion of cutting-edge software and hardware that could redefine control systems worldwide. But the most striking example of collaboration might be ITER, the International Fusion Reactor project in France. While primarily focused on energy, its research into containing star-like plasma directly informs spacecraft propulsion. Scientists from 35 nations contribute data, proving that the line between earthly fusion reactors and interstellar engines is thinner than we think. This spirit of cooperation isn't just altruistic, it's pragmatic. Space agencies now routinely share test results through forums like the International Electric Propulsion Conference, recognizing that solving plasma's puzzles, whether erratic ionization or magnetic field instability, benefits everyone. When Japan's microwave-powered thrusters demonstrate unprecedented longevity, or India's small-sat innovators miniaturize plasma systems for CubeSats, the entire field leaps forward. The result, a growing library of shared knowledge that turns once impossible missions, like crewed flights to the outer planets, into engineering challenges rather than fantasies. Yet beneath this unity lies friendly competition, the kind that fuels innovation. The US and Europe might lead in high-power electric propulsion, but China's rapid prototyping or Russia's rugged thruster designs force others to adapt faster. This dynamic mirrors the golden age of aviation, when rival nations spurred each other to conquer the skies, except now, the stakes include sustainable access to the solar system. Private companies add another layer, with startups from Berlin to Bangalore racing to patent novel thruster geometries or alternative propellants like iodine. The winner isn't any single country or corporation, but a future where humanity's expansion into space is no longer limited by the propulsion systems of the past. The implications stretch far beyond technology. Shared propulsion research builds diplomatic bridges, creating interdependencies that discourage conflict. When a French plasma lab relies on Japanese superconducting magnets, or an American lunar lander uses Russian throttleable thrusters, space becomes a neutral zone where collaboration outweighs competition. This model might one day extend to joint interstellar probes, where international crews could share not just spacecraft but the very plasma drives that carry them toward alien suns. The message is clear: the engines of tomorrow won't belong to one flag, they'll bear the insignia of Earth. There's a reason plasma engines feel like they've been ripped from the pages of a sci-fi novel. They tap into humanity's oldest dream, touching the stars. Unlike clunky chemical rockets or even sleek solar sails, plasma propulsion carries an almost mythical quality. It's not just technology, it's alchemy, turning the raw stuff of lightning and solar flares into engines that could outlast civilizations. This isn't accidental. For decades, popular culture has primed us to see plasma as the epitome of advanced tech, from Star Trek's warp cores to the glowing drives of the expanse. When real-world scientists talk about harnessing star power, it resonates because we've already imagined it 1,000 times over. This cultural groundwork matters more than you might think. Public fascination translates directly into funding and political will. Remember the moonshot era? Kennedy didn't just sell Congress on cold calculations. He sold a vision, one that plasma propulsion now inherits. Documentaries like Netflix's Return to Space frame ion thrusters as the quiet heroes of modern exploration, while YouTube creators break down plasma physics with visuals of swirling blue exhaust that could double as special effects. The result, a generation of engineers and voters who see this not as niche science but as humanity's inevitable next step. Even SpaceX's viral Starship test flights, though methane-powered, borrow plasma's aesthetic. Those shimmering engine plumes are no coincidence. They're selling a future we've already been conditioned to crave, but the relationship between perception and progress isn't one way. Every real-world breakthrough, like NASA's successful Vasima tests or China's lunar plasma experiments, feeds back into the mythos, creating a virtuous cycle. When the European Space Agency announced its intention to use ion thrusters for a Mars sample return mission, headlines didn't dwell on kilowatts or specific impulse. They declared Earth to Mars on star power. That narrative sticks. It's why billionaire investors pour millions into fusion startups like Helion, and why congressional appropriations for advanced propulsion research often pass with rare bipartisan support. Nobody wants to be the politician who stalled the future, yet there's a delicate balance at play. Overhyping plasma's near-term potential risks backlash when timelines slip. See the fusion energy roller coaster for cautionary tales. The key lies in tempering wonder with transparency. Scientists like Dr. Franklin Chang Diaz, who spent years developing the Vasima engine while starring in documentaries, exemplify this. They celebrate plasma's cosmic promise while openly discussing the decades of gritty engineering ahead. It's a dance between inspiration and realism, one that keeps the public engaged without disillusionment. What's often overlooked is how this cultural momentum shapes education. Universities report surging enrollments in aerospace programs whenever plasma milestones go viral. High school students build miniature ion thrusters for science fairs. Their designs gleaned from YouTube tutorials. This grassroots enthusiasm doesn't just fill labs with fresh talent. It ensures that the next generation of breakthroughs won't hinge on a handful of geniuses, but on a global movement of minds raised on the idea that starships aren't fantasy. The most powerful thing about plasma engines might not be their exhaust velocity, but their ability to turn dreamers into engineers, and that's a kind of propulsion no equation can quantify. The very nature of plasma propulsion, unlimited endurance, extraordinary efficiency, carries an ethical weight as immense as its potential. Unlike traditional rockets constrained by fuel limits, these engines could grant near-permanent presence in space, reshaping not just how we explore, but who controls access to the cosmos. This isn't merely a technical leap, it's a societal pivot point. The same thruster that might one day ferry climate scientists to Mars could also power orbital weapons platforms or corporate monopolies over celestial resources. The question isn't whether plasma technology will be transformative, it's whether humanity can steward that transformation wisely. History offers sobering parallels. The nuclear age began with promises of limitless energy, yet birthed existential threats that still haunt us. Space, however, presents a unique dilemma. No borders, no clear governance, and resources so vast they could either unite nations or ignite conflict. Asteroid mining alone illustrates the tension. A single platinum-rich space rock could destabilize global markets, and the entities controlling plasma-driven mining fleets would wield unprecedented economic power. Without frameworks ensuring equitable access, we risk replicating Earth's inequalities on a cosmic scale. The Outer Space Treaty of 1967 provides a foundation, prohibiting national claims on celestial bodies, but says little about private corporations or multilateral exploitation. As plasma propulsion turns theoretical mining into imminent reality, these gaps in governance grow more urgent. Weaponization looms equally large. Plasma engines' stealth and endurance make them ideal for military applications, surveillance satellites that never leave their posts, or agile drones capable of disabling adversaries' spacecraft without a trace. While major powers currently avoid deploying weapons in space, the line between defensive and offensive systems blurs quickly. A satellite equipped with plasma thrusters could evade an attack just as easily as it could position itself to sabotage another nation's assets. The lack of visible exhaust makes attribution nearly impossible, turning potential conflicts into murky, deniable confrontations. Initiatives like the European Union's proposed space traffic management framework aim to mitigate such risks, but enforcement remains a thorny challenge when technology outpaces diplomacy. Yet for all these risks, plasma propulsion also presents unparalleled opportunities for global cooperation. Consider climate monitoring. Fleets of plasma-powered satellites could track deforestation, methane leaks, or ice melt with unprecedented precision, providing neutral data to guide international policy. Or take disaster response. Engines that never exhaust their fuel could position supply caches in orbit, ready to deploy aid anywhere on Earth within hours. The key lies in institutionalizing transparency. Open-source propulsion designs, like those pioneered by academic consortia, could democratize access while reducing fears of covert arms races. Models exist. The International Space Station's collaboration among former Cold War rivals proves shared infrastructure in space is possible, even among geopolitical rivals. The path forward demands proactive ethics, not reactive fixes. Scientists developing plasma thrusters must engage with philosophers, policymakers, and the public to embed values like equity and sustainability into the technology's DNA. Analogies abound. The Montreal Protocol's success in healing the ozone layer shows how preemptive treaties can avert catastrophe. Similarly, a plasma protocol could establish norms, perhaps mandating that a percentage of space-derived resources fund global development, or creating neutral zones around celestial bodies like Mars to prevent territorial grabs. Private companies, too, must adopt voluntary restraints, much as biomedical firms oversee gene editing research. What makes this moment pivotal is the narrowing window to act. Plasma propulsion is transitioning from lab curiosity to operational reality, and the rules written in the next decade will echo for centuries. The choice isn't between progress and caution. It's about shaping progress to reflect humanity's highest aspirations rather than its oldest rivalries. The engines themselves are neutral. Their legacy depends entirely on the hands and the values guiding them. Plasma propulsion isn't just revolutionizing space travel, it's igniting a fire in classrooms and research labs around the world. Walk into any cutting-edge aerospace engineering program today, and you'll find students huddled around miniature ion thrusters, their faces lit by the same blue glow that powers deep space probes. Universities like MIT and Stanford have transformed plasma physics from an abstract elective into a hands-on discipline, with undergrads building functional thruster prototypes using off-the-shelf components. The message is clear: this isn't distant future tech anymore. It's a career path waiting to be claimed. What makes plasma so uniquely inspiring for young scientists is its tangible connection to the cosmos. While traditional rocketry relies on brute force chemistry, plasma propulsion mirrors the elegant forces shaping stars and nebulae. Outreach programs capitalize on this wonder. The European Space Agency's Plasma Camp lets high schoolers create miniature auroras in vacuum chambers, while NASA Jet Propulsion Laboratory hosts summer workshops where teens guide scale model satellites using ion thrusters. These experiences do more than teach physics. They reframe space exploration as something participatory, showing students they could one day design the engines that carry humanity to Mars. The ripple effects extend far beyond campus labs. YouTube creators like Alpha Phoenix and Veritasium have turned plasma demonstrations into viral phenomena, with tabletop experiments showcasing how ionized gas bends to magnetic fields. One viral video of a home-made Hall effect thruster, built by a 19-year-old community college student, racked up millions of views and inspired countless replicas. This democratization of knowledge is critical. When a teenager in Nairobi can access MIT's open courseware on plasma physics or join international forums discussing thruster designs, the barriers to entry crumble. The next breakthrough might not come from a government lab but from a dorm room in Jakarta or a garage in Buenos Aires. Teachers are leveraging this excitement to reshape STEM curricula. Gone are the days of dry textbook diagrams explaining rocket nozzles. Today's students calculate exhaust velocities for hypothetical Mars missions, debate the merits of xenon versus argon propellants, and even compete in university challenges to optimize thruster efficiency. Competitions like the Caltech Space Challenge routinely feature plasma propulsion scenarios, tasking undergrads with designing missions to Ceres or Europa using real-world engine specs. These aren't academic exercises, they're proving grounds for the engineers who'll staff private space firms and national agencies in the coming decade. Perhaps the most profound impact lies in diversity. Plasma's interdisciplinary nature, merging physics, engineering, and computer science, draws in students who might never have considered aerospace careers. At the University of Michigan, a pioneering program recruits women and underrepresented minorities into plasma research by framing it as climate science. highlighting how clean propulsion could reduce space debris and orbital pollution. The approach works. Enrollment in their electric propulsion courses has tripled in 5 years, with graduates funneling into companies like SpaceX and Blue Origin. The ultimate testament to plasma's educational power might be its storytelling potential. When a middle schooler watches NASA, a Dawn spacecraft powered by ion thrusters, send back images of the dwarf planet Ceres, they're not just seeing science. They're witnessing the payoff of persistence, innovation, and sheer curiosity. That emotional resonance is priceless. Museums from Tokyo to Chicago now feature plasma exhibits where kids can pilot virtual spacecraft using touchscreen controls, their trajectories dictated by real propulsion physics. These experiences plant seeds that could grow into lifelong passions. We're standing at the threshold of a generational shift. The students tinkering with plasma today will be the ones deciding whether fusion drives take us to Alpha Centauri or how to regulate asteroid mining operations. Their education isn't just about equations and lab reports, it's about cultivating the imagination to wield star power responsibly. And that might be plasma propulsion's most enduring legacy. Not the engines we'll build, but the minds we'll inspire to build them. For all their potential, plasma engines still face obstacles as vast as the distances they aim to cross. The most immediate challenge: power, and lots of it. While solar panels work beautifully for satellites orbiting Earth, they become useless beyond Mars, where sunlight dwindles to a faint glow. Nuclear reactors could bridge this gap, but scaling them down for spacecraft without adding dangerous weight remains a puzzle even the brightest minds haven't cracked. Consider the numbers. A high-thrust plasma engine for a crewed Mars mission might demand several megawatts, equivalent to powering a small town. Where that energy comes from and how to store it safely in the void of space is a hurdle we're still learning to leap. Then there's the blistering heat. Plasma doesn't just generate thrust, it radiates temperatures exceeding the surface of the sun, enough to melt conventional engine components in seconds. Labs worldwide are racing to develop materials that can withstand this inferno. Tungsten and ceramic composites show promise, but they bring their own headaches: brittleness, weight, and the tendency to crack under repeated thermal stress. Some engineers are experimenting with active cooling systems, where liquid metals swirl through microscopic channels in the engine walls, absorbing heat like a high-tech bloodstream. Others are rethinking the entire architecture, designing magnetic nozzles that never physically touch the plasma at all. Every solution, though, adds complexity to systems that must remain reliable for years in the unforgiving vacuum of space. Material science isn't the only bottleneck. Funding cycles move at a glacial pace compared to the breakneck speed of innovation. While private companies like SpaceX can pivot quickly, government programs, often the backbone of deep space research, face bureaucratic delays that stall progress for years. The story of NASA Prometheus project tells it all. A promising nuclear electric propulsion initiative cancelled in 2005 due to shifting priorities, only for its ideas to resurface a decade later under new branding. This stop-start dynamic isn't just frustrating, it scares away top talent who might otherwise dedicate careers to plasma research. Yet the greatest roadblock might be psychological. After decades of chemical rockets, the aerospace industry is wired for incrementalism, tiny improvements to existing systems rather than radical reinvention. Convincing mission planners to bet on unproven plasma technology for billion-dollar projects requires more than data. It demands a cultural shift. The Dawn spacecraft's success with ion thrusters helped, but high-profile failures loom large in institutional memory. When the European Space Agency's BP Colombo suffered temporary thruster glitches en route to Mercury, critics pounced, ignoring that its plasma engines ultimately saved the mission by compensating for earlier issues. Overcoming these barriers will take more than brilliant engineering. It'll require a new model of collaboration. Imagine materials scientists working alongside fusion researchers, sharing insights on magnetic confinement. Picture aerospace giants pooling resources with startups nimble enough to test wild ideas. The International Space Station offers a blueprint, 15 nations combining expertise to build what none could alone. Apply that spirit to propulsion, and suddenly the challenges seem less like walls and more like stepping stones. The stakes couldn't be higher. Solve these puzzles, and we unlock engines that could tour the solar system on a single fuel load, slingshotting probes to Pluto in years instead of decades, or enabling crewed outposts on Mars with regular supply lines. Stall now, and we risk ceding the future to those bold enough to embrace plasma's potential first. The technology won't mature by accident. It'll take sustained vision, investment, and the collective will to reach beyond the tried and true. That's the price of rewriting the rules of spaceflight, and the reward is nothing less than the keys to the cosmos. 50 years from now, the spacecraft cruising our solar system might bear little resemblance to today's roaring chemical rockets. Instead, they'll glide silently on streams of superheated plasma, their engines humming with the same primordial energy that lights distant stars. Picture a bustling interplanetary highway where cargo tugs haul mined asteroids toward lunar refineries, their plasma thrusters burning not for minutes but for years without pause. Crude ships bound for Mars could make the trip in weeks rather than months, their fusion-powered drives shrugging off the tyranny of fuel limits that once shackled human ambition. This isn't speculative fiction, it's the logical endpoint of breakthroughs already unfolding in labs from California to Shanghai. The real game changer will be fusion. While today's ion thrusters are marvels of efficiency, they're still limited by external power sources like solar panels or nuclear reactors. But imagine a future where the engine itself is the power plant, fusing hydrogen atoms into helium and channeling the resulting plasma into thrust. Companies like Helion and TA Technologies are already racing to commercialize compact fusion, and their success could redefine propulsion entirely. A Mars-bound vessel equipped with such a system wouldn't just carry fuel, it would harvest it from space itself, skimming hydrogen from the solar wind or mining ice deposits on passing comets. The line between propulsion and sustainability would blur, turning every mission into a self-sustaining journey rather than a one-way gamble. Asteroid mining operations will likely be among the first to capitalize on this revolution. Today, the idea of extracting platinum or rare earth metals from space rocks is hampered by the exorbitant cost. Chinese letter. Plasma engines change that equation. Robotic miners equipped with high-efficiency thrusters could hop between asteroids with the ease of taxis shuttling between city blocks, their endurance limited only by the wear on their components. Startups like Astroforge are already planning missions to test extraction techniques, but the true boom will come when plasma propulsion slashes the price of moving raw materials. Lunar factories could process ore into fuel or construction materials, creating an off-world supply chain that fuels further exploration. The economic ripple effects would dwarf the gold rushes of Earth's past, with entire industries born from the ability to go farther and stay longer. Interstellar travel, once the exclusive domain of thought experiments, could inch toward reality. Breakthrough Starshot's laser-driven microprobes might pave the way, but crewed missions demand something more robust. Here, pulsed plasma propulsion like that envisioned in Project Orion's nuclear pulse designs could offer a solution. By detonating fusion pellets behind a spacecraft and channeling the resulting plasma into a magnetic push plate, such systems could theoretically reach a tenth of light speed. The ethics are thorny, but the physics is sound. Within 50 years, we might see uncrewed probes departing for Proxima Centauri, their plasma trails etching humanity's signature across the light years. The most profound shift, though, could be cultural. As plasma engines democratize access to space, the monopoly held by superpowers and billionaires will fracture. Universities might launch their own deep space telescopes, while developing nations deploy climate monitoring satellite networks without relying on foreign rockets. The Artemis Accords governing lunar exploration could evolve into a framework for shared propulsion standards, ensuring no single entity controls the highways between worlds. This isn't just about technology, it's about rewriting the social contract of spacefaring civilization. Yet for all this promise, the path won't be linear. Materials that withstand decades of plasma bombardment, regulatory frameworks to prevent orbital monopolies, and the sheer engineering audacity required to tame star power, all these hurdles remain. But history shows that when the right tools meet urgent need, progress accelerates exponentially. The next 50 years won't just witness incremental improvements to plasma engines. They'll define whether humanity becomes a multi-planet species or remains tethered to Earth. The engines of the future aren't waiting to be invented. They're sparking to life in vacuum chambers today, their blue glow a beacon to the cosmos beyond. Plasma propulsion has been trapped in a strange paradox, simultaneously dismissed as science fiction and exaggerated as classified super technology. The truth, as usual, is far more interesting than either extreme. Let's start with the most persistent myth, that plasma engines are just lab curiosities with no real-world use. Tell that to the dozens of satellites silently adjusting their orbits right now with ion thrusters, or NASA's Dawn spacecraft, which spent 11 years exploring the asteroid belt on a single tank of xenon fuel. These aren't prototypes gathering dust, they're workhorses of modern spaceflight, proving plasma propulsion isn't just viable, but often superior to traditional methods for specific missions. Then there's the opposite misconception, that shadowy government agencies already have warp-capable plasma drives hidden away. While it's true that militaries invest in advanced propulsion, like the Air Force's enigmatic X-37B spaceplane, the reality is far less cinematic. Plasma engines follow the same laws of physics as everything else. No amount of secrecy can magically overcome the energy requirements for instantaneous travel or defy the tyranny of the rocket equation. The most exotic confirmed projects, like Ad Astra's Vasima engine, are publicly documented and subject to the same painstaking testing as any aerospace technology. The gap between Hollywood's imagination and actual engineering becomes obvious when you consider the heat management challenges alone. Containing plasma at sun-like temperatures isn't something you can hide in a Nevada hangar. It leaves trails of published research, patent filings, and international conference presentations. Another common oversimplification is that plasma engines will replace chemical rockets entirely. This ignores the fundamental trade-offs of propulsion systems. Yes, plasma thrusters are exponentially more fuel efficient, but they generate far less instantaneous thrust. No plasma engine today could lift a spacecraft off Earth. That still requires the raw power of chemical combustion. The future likely lies in hybrid systems, traditional rockets for launch, plasma for the long haul. Think of it like a cross-country road trip. You wouldn't use a Tesla to climb a sheer cliff face, but you'd absolutely choose it over a gas guzzler for the interstate. Each technology excels in its niche. Perhaps the most dangerous myth is the assumption that plasma propulsion will magically solve all the challenges of space travel. While it dramatically reduces fuel needs, it introduces new complexities like the megawatts of power required for high-thrust operation or the delicate balance of magnetic containment. These aren't trivial hurdles. The International Space Station's entire solar array, spanning an acre, generates only about 100 kilowatts, a fraction of what a crewed Mars mission would need. Until we crack compact fusion or revolutionary power storage, even the best plasma engines will remain constrained by energy economics. Yet dismissing these challenges as deal breakers misses the bigger picture. Every transformative technology has its awkward adolescence. The first steam engines were laughably inefficient compared to horses until they weren't. The Wright brothers' flyer couldn't cross a football field until aviation could span oceans. Plasma propulsion is in its Wright flyer phase, and that's exhilarating. The satellites using it today are the proof of concept, the stepping stones to the fusion-powered starships of tomorrow. The key is tempering wonder with patience. When social media proclaims plasma engines will take us to Mars next year, it does real harm by setting unrealistic expectations that fuel disillusionment. Progress happens in increments, a slight increase in thrust efficiency here, a new superconducting magnet design there. What looks like slow motion in headlines represents countless engineers wrestling plasma into obedience one equation at a time. So where does this leave us? Not with fantasies of instant warp speed, but with something better. A technology grounded in real achievement yet brimming with untapped potential. The satellites silently gliding on ion thrusters today are the harbingers of a future where the solar system becomes our backyard, not because of magic, but because humanity learned to harness the same force that lights the stars. That's a story far more compelling than any myth. You might be surprised to learn that some of the most fascinating plasma experiments aren't happening in multimillion-dollar labs. They're taking place in garages, classrooms, and backyard workshops. Take the humble plasma globe, that mesmerizing desk toy that shoots purple tendrils of light to your fingertips. What feels like magic is actually a window into how ionized gases behave under electric fields. Crack one open safely, of course, and you'll find nothing more complex than a high-voltage electrode surrounded by low-pressure gas, the same basic ingredients powering advanced thrusters, just scaled down for your coffee table. For those craving a deeper challenge, building a Farnsworth-Hirsch fusor offers a thrilling next step. This tabletop device, first conceptualized by a teenage fellow Farnsworth in the 1920s, uses electrostatic fields to squeeze deuterium gas into a glowing plasma ball at its center. Modern hobbyists construct them from recycled microwave oven parts, vacuum chamber fittings, and patience. While these homemade fusors won't achieve net positive fusion despite viral YouTube claims, they make stellar science fair projects literally. Watching that eerie blue plasma core flicker to life isn't just cool. It's a masterclass in how charged particles behave under confinement, mirroring the principles behind industrial plasma reactors and experimental fusion devices. What makes amateur plasma tinkering so valuable isn't just the hands-on learning, it's the unexpected discoveries bubbling up from citizen scientists. Consider the case of high school students in Norway who modified a plasma globe with custom electrodes, stumbling onto a novel way to stabilize plasma filaments. Their findings, later published in a peer-reviewed journal, caught the attention of aerospace engineers studying thruster erosion, or the global network of fusor enthusiasts sharing data on neutron emissions, collectively contributing to our understanding of low-energy nuclear reactions. Platforms like the open-source Fusor Research Consortium have turned basement experiments into collaborative research nodes, proving you don't need a budget to advance plasma science. Safety, of course, is non-negotiable. Working with high voltages and vacuum systems demands respect, proper grounding, radiation monitoring for fusers, and never bypassing safety interlocks. But with precautions in place, the barrier to entry is lower than you'd think. Kits like the Plasmaduino let beginners explore glow discharges safely, while university outreach programs often loan professional-grade equipment to STEM clubs. Even smartphone apps have joined the party, using their cameras to analyze plasma spectra through diffraction grating films, suddenly identifying the elemental composition of that neon sign. Plasma becomes as easy as snapping a photo. The ripple effects extend beyond education. Amateur plasma experiments are quietly reshaping how we crowdsource innovation. Projects like Stellar Net's DY spectroscopy challenges have led to improved methods for detecting plasma impurities, techniques now used in semiconductor manufacturing. When a retired electrical engineer in Texas devised a cheap method to measure electron temperatures using modified laser pointers, the trick spread through online forums and eventually into university labs. This two-way flow of knowledge underscores a profound truth. Plasma physics isn't some ivory tower discipline. It's a living science, thriving wherever curiosity meets a spark of high voltage. So whether you're a teacher demoing plasma conduction with a pickle, yes, electrified pickles glow due to sodium-ion plasma, a student 3D printing a mini magnetoplasmadynamic thruster, or just someone fascinated by the fourth state of matter, remember every major leap in plasma technology started with someone asking, "What happens if I try this?" The next big idea might not come from a government lab, but from a well-worn workbench where passion and high voltage collide. The dream of plasma-powered spaceflight isn't just for scientists in lab coats, it's a future we can all help build. Right now, universities and research centers are pushing the boundaries of what's possible, but they're often strapped for resources. Take the Princeton Plasma Physics Laboratory, where breakthroughs in magnetic confinement could revolutionize propulsion, yet their budget is a fraction of what's spent on traditional aerospace projects. That's where public support comes in, donating even the cost of a coffee to organizations like the Planetary Society or Ad Astra Rocket Company directly funds graduate students tweaking thruster designs or engineers testing new materials to withstand plasma's fury. These aren't abstract contributions, they're the nuts and bolts of progress. Advocacy might sound daunting, but changing the trajectory of space funding can start with a single email or social media post. When NASA budget hearings roll around, lawmakers pay attention to constituent voices, especially those passionate about advanced propulsion. Remember the viral campaign that saved the James Webb Space Telescope from cancellation? Public pressure works. Joining space advocacy groups like the National Space Society amplifies your voice, turning individual enthusiasm into collective clout. And it's not just about government funding. Tagging companies like SpaceX or Blue Origin in posts about plasma research reminds billionaires where their investments could spark the next big leap. For those who prefer hands-on involvement, citizen science platforms offer unexpected opportunities. Projects like Zooniverse's Plasma Zoo let volunteers analyze real thruster test data from home, helping researchers spot patterns even algorithms miss. Or consider crowdfunding campaigns like the one that funded MIT's experimental mini-fusion reactor, raising $200,000 from small donors. These efforts prove you don't need a PhD to advance plasma science, just curiosity and a willingness to pitch in. Students have a unique role to play. Pressuring universities to expand plasma physics electives or starting rocketry clubs focused on electric propulsion plant seeds for tomorrow's breakthroughs. The University of Michigan's student-built ion thruster, which recently outperformed commercial models in efficiency tests, began as a dorm room brainstorm. Now its patented technology, the ripple effects of public engagement go beyond dollars and data. When researchers see communities rallying behind their work, it fuels the perseverance needed to tackle problems that might take decades to solve. Every shared article, every classroom demonstration, every call to a congressional office adds momentum. Plasma propulsion isn't just transforming how we travel through space, it's redefining who gets to shape that journey. The engines of the future won't be built by a select few in secret labs. They'll rise from the collective will of everyone who dares to reach for the stars. Plasma engines aren't just another incremental upgrade, they're a fundamental rewrite of what propulsion can be. Think about it, every major leap in human exploration has been tied to how we move. The invention of sails opened the oceans, steam engines shrank continents, and chemical rockets gave us the moon. Now, plasma propulsion stands poised to unlock the solar system, not with brute force, but with the elegant persistence of a technology that could outlast its creators. This isn't merely about going faster or farther, it's about redefining the very economics of spaceflight. Consider how radically this shifts our timeline for exploration. Traditional missions operate on a scarcity mindset, every gram of fuel rationed, every maneuver calculated to the last drop. Plasma thrusters flip that script. A probe equipped with one of these engines could tour Jupiter's moons, swing past Saturn's rings, and still have enough fuel left to chart the Kuiper belt, all on a single mission. The Dawn spacecraft gave us a preview, visiting 2 asteroids with fuel to spare, but that's just the appetizer. Imagine a future where spacecraft aren't disposable one-shot wonders, but enduring assets, their value compounding over decades of service. What makes this moment so electrifying is the convergence of breakthroughs happening across disciplines. Superconducting magnets, once confined to massive lab installations, are now being miniaturized for spacecraft. Artificial intelligence algorithms can predict and counteract plasma instabilities faster than any human engineer. Even the rise of private space companies plays a role. Their willingness to take risks on unproven technologies accelerates progress in ways government programs alone can't match. Each innovation is a puzzle piece, and when they click together, the picture they reveal is extraordinary. Engines that could theoretically run for centuries, limited only by the wear on their components and the persistence of their power sources. Yet for all their promise, plasma engines demand something equally vital from us: patience. The Wright brothers' first flight lasted 12 seconds. It took 66 years to land on the moon. The timeline for plasma propulsion will likely follow a similar arc of incremental triumphs and setbacks. Early adopters will face skeptics asking why we're investing in technology that can't yet lift a rocket off the pad. The answer lies in the long game. Chemical rockets brought us to space, but plasma will let us stay there, turning precarious outposts into sustainable frontiers. The most inspiring part, this revolution isn't happening in some distant future. It's unfolding now, in university labs where students 3D print thruster components, in startup garages where engineers test radical new confinement geometries, and in international collaborations that share data across borders. You don't need to wait for a headline-grabbing Mars mission to see progress. It's there in the quiet hum of ion thrusters adjusting satellite orbits overhead, in the blue glow of experimental reactors, and in the growing community of minds determined to crack these challenges. So where does this leave us? Not at an ending, but at a threshold. The engines of tomorrow won't roar, they'll whisper, their plasma trails etching invisible highways across the solar system. They'll carry robots to mine asteroids, telescopes to peer past the Oort cloud, and perhaps one day, families to homestead on distant worlds. The obstacles ahead are real, but so is the momentum. Every test firing, every simulation, every prototype that survives 100 hours of continuous operation brings that future closer. This isn't just about building better machines. It's about choosing what kind of civilization we want to be, one content with brief excursions beyond Earth, or one that embraces the stars as its birthright. Plasma propulsion offers a path to that second future where the word impossible loses its grip on our ambitions. The journey will demand creativity, resilience, and collective will, but the destination, a solar system humming with human activity, its vastness made navigable by engines that never stop, is worth every challenge. The age of plasma has arrived. Our task now is to meet its potential with the audacity it deserves.